speaker is Andy Collard with NCEP, the Environmental Modeling Center, and going to talk about how upper air data is used by NCEP. So Andy, go right ahead.
I guess I need to share my screen, don't I?
Oh, you don't think about normally from a regular weather area. So.
Yes, it sounds like a pressure cooker of a job.
Yes, it definitely can be. There's quiet times and then thunderstorms around and emergencies and other craziness can really be insane, especially with usually only one forecaster on at a time. So there's usually, not a lot of help and you're just running ragged. So.
All right, it looks like we're almost there with that. So I'll ask one more quick question for you there, Mindy. On day one, Marin mentioned that the NWS was trusted by partners. Is that your experience? And you get to deal with some pretty high-profile folks here with all of the carriers that we have. So, yeah, what is their perception?
So far, I think all their perception has been, that they're grateful for the work that we do. They're grateful for the information we provide, and definitely, take the fact that we're embedded and they're kind of providing them their service, and especially even working with all the extra the UPS and the FedEx meteorologists and stuff. It really is a look into the weather enterprise and how we all work together to serve the partners. And so I really like that aspect and think that they've all had positive feedback.
All right, fantastic. I think we've got it now. So, and yeah, and we got two Andrews, so outstanding. So go right ahead and take it away. And you're muted on both, just so you know.
Okay. Can you hear me now?
Okay. Yep, we got you.
Okay. And can you see my presentation?
We can see your presentation. You're in the kind of the presentation mode instead of the. There you go. Yeah, if you do that, we'll be able to follow along. So go right ahead.
Okay. All right. Let's. Apologies for that. It's pretty bad when my technical skills let me down in one of these talks. I'm Andrew Collard. I'm at the, as mentioned, I'm at the Environmental Modeling Center at NCEP. We're the people that do the development of all of the operational numerical weather prediction systems at NOAA. And I'm going to take you on a whistle-stop tour of data assimilation, how we use observations in general, and of course a little bit of a focus on upper air. So my next slide is, this is just a summary of my talk. I'm going to talk about how we use upper air observations in data assimilation, and a little bit on the impact of the upper air observations and a summary. So data assimilation is about combining our best knowledge of the atmosphere from various different sources. So we try to create what we call an analysis of the atmosphere, which is the best possible state, the most probable state of the atmosphere based on current observations, information from prior observations that we use the model to bring us up to the current time, and our knowledge of, obviously our physical knowledge of how the atmosphere works, and our knowledge of the errors. So one of the things you always need to think about with data assimilation is the analysis and the forecast runs is not just is not just using the information from the current time. It's using observations all the way back through that the model is actually propagating that information forward. Therefore, we think the analysis is a very, very good approximation of what the atmosphere looks like, because it's basically a combination of observations throughout history. And the way we use the observations is we adjust the model so that it agrees more closely with the observations that are being presented to it. In some cases, such as radiosondes, that's primarily you just have to interpolate the model to the observation location and do a comparison. Other types of observations like satellite radiances or GPRO bending angle measurements are a lot more complicated to do that mapping between the observation and the model. We try to avoid, and this is not really relevant to the upper air, but we try to avoid creating pseudo observations from real observations. So we don't take a radiance observation of the Earth, turn it into a radiosonde-like profile and assimilate it. What we do is directly compare radiances with modeled radiances from the model. So how do we do that? It's basically a weighted least squares. If we can see on this, what we're trying to do is minimize this X, which is the current state of the atmosphere. X is a very, very long vector, and it describes temperature, humidity, winds, etc. throughout the entire atmosphere, horizontally and vertically. And we try to make this X such that the observations, which are called Y, agree with the modeled observations, which we call H of X. And at the same time, this is XB. The XB is the background. That's normally a short-range forecast. That was our best guess of what the atmosphere looked like before we confronted it with observations. And because everything has errors, the observations and the background, we're trying to balance the information we already know from the background with what we've been presented with the new observations. I know I'm being very fast through this, but one thing I want to bring out on this is the one thing from the observational side in DA is this comparison between the observations and the modeled expectation of what the observations is, which I call here is Y minus HX. We call that the observation error departure, the observation departure. And that is normally the basis of most of the quality control that we do. So this is a little more complicated than it possibly needs to be in this case. This is showing how we do data assimilation in the GFS, in the global forecasting system. Most forecasting systems are similar. We start with a deterministic forecast here in the top left corner, which is normally a 6-hour forecast from the previous analysis. And that goes into the GSI, our grids point statistical interpolation model. That's our data assimilation model. It's got a rather kooky name. And then here we have, and what we do is in here, we compare the observations, which are down here, with the 6-hour forecast, and we come up with an increment. That's how much do we have to nudge the model to get a much better agreement between the observations and the new model. This is the analysis increment. That then creates a new analysis. Then you run the forecast model again, and that's where the forecast starts from. It goes forward in time. But that same short-range forecast is then used for the next cycle to start it all over again. So we're constantly creating an analysis, pushing it forward through time, comparing with observations, creating a new analysis, and pushing it forward in time. That is the cycle. All of this stuff down below is about how do you estimate the errors in the analysis, and that's beyond the scope of this talk. We use a lot of observations. This is the other thing I'm trying to make clear from this talk, is we use a very large number of observations. The upper air radiosondes are part of a much larger ecosystem. These are what we call conventional observations. It's kind of a strange category, but it's generally referring to observations that are some sort of variant of temperature and humidity, and they're mostly in situ. We have an awful lot of these from, as you see, a lot of different sources: radiosondes, aircraft, some surface obs, scatterometer measurements. And then we also have a lot of radiance measurements. So I'm just going to show, this is sort of the typically what we assimilate in a typical cycle. So here you see the surface obs and the radiosondes. Surface obs are ubiquitous all around the globe, at least on land. with a few sea observations. Radio sondes, a little less evenly spread around the globe, obviously the US and Western Europe, China, but some parts of the globe, especially the southern hemisphere, are very, very devoid in observations from radio sondes. So if you want, especially if you want the upper air measurements, you need other observations to take over. And then, so here you can see, for example, on the left, you have the geostationary winds that are derived from the geostationary satellites, just tracking cloud features or water vapor features. That gives you pretty good coverage around most of the globe. There's a sort of an area around the poles, which is a little less well covered, but that gives you some wind information. Aircraft obviously help you cover a little bit more. That's all, but that's obviously mostly limited to the flight heights, except for at airports. And then we have, again, these are well beyond the scope of this talk, but the polar radiance observations, which are a huge part of our system as well. And that allows you to cover virtually the whole globe within a 6-hour period through these various microwave and infrared remote sensing. So I was asked, this is one slide on quality control, how we do quality control in the in our system. I had quite a big deep dive on this, and I decided that it's easiest just to summarize it in one slide. I've put down an office note which talks about some of the CQC, the complex quality control that we do. The PREP CQC code, which is the bulk of the pre-processing quality control, is 30,000 lines long, but it's summarized here. Almost every check, apart from real gross checks looking for things which are obviously unphysical, like 1,000-degree temperatures or really obvious errors, most of the checks rely on that first guess departure statistic that I referred to earlier. They are, you want to compare what we think is the best guess of the atmosphere, which is our 6-hour forecast, compare that with the observation, and then look for discrepancies. And you can have, the first order, first guess departure checks where you're looking at, does a temperature observation differ by 3 Kelvin from the model? That's telling you there's probably something wrong. And then you actually dig deeper in that and actually say, well, we actually compare the first guess departures, but are they consistent horizontally between adjacent observations? Are they consistent in the vertical? And then there's other checks. We want to make sure that the hydrostatic residuals are correct, with that there's not some issue with the hydrostatic calculations. We look for stuck values. If the value is repeating over and over again, that says there's something probably wrong. We have lapse rate checks. We have buddy checks. And then we also finally have, within the actual data assimilation itself, within the minimization, the solving of that equation, we have variational quality control, where observations, if they initially disagree with the model, but if enough observations disagree in the same way, they're actually allowed to come back in, even if initially they were rejected for disagreeing with the model too much. The other really important, the one really important thing I want to talk about for radiosondes and how we use them is they are an anchor, because most of the observations that we assimilate, especially the radiance observations, which are a huge amount of our model, they are bias corrected. There are various sources of bias in the observations, and we actually need observations that we can trust to be unbiased, because the bias correction basically compares the observation to the model, and if there's not something anchoring the model, the bias correction can drift off into strange places. So upper air data is very, very important in how we use the radiances, and in that way, they're indirectly not just causing their own impact, but impacting how we use everything else. So I borrowed this from ECMWF because they have better slides than we do. I used to work there, so I think I'm allowed to do that. This is about a week's worth of first guest departure measurements for radiosondes in the mid-troposphere. And just to show you, give you an idea, this is how far, if I showed a plot for us, it would look very, very similar. This shows on average how much the radiosonde observations are differing from what we thought was our best first guess, the analysis. Sorry, the 6-hour forecast. And you can see, generally we do a pretty good job. Most observations are within a Kelvin of the model themselves. And I'll just show you what happens. We have information here. Some of this is error, some of this is information. And so you can see as we do the minimization, the agreement between the radiosonde and the model is much, much better. So this is what we're doing every cycle. We're just nudging the model to just agree slightly better with the observations. So you can see that's like a typical way that that we're improving our knowledge of the atmosphere through the radiosondes. Impact of upper air observations on forecasts. Now, most of the time I give talks to data providers. They're very excited about how large their impact from their observations are because they're obviously the most important observations in the system. Upper air observations probably are the most important observations in the system. But before I show this, just bear in mind, all of these observations are part of a much larger ecosystem, and there's a lot of information that's redundant between them. So we don't often do actual data denials of the radiosondes, and the closest I've got is this from almost 10 years ago now, and it just shows the relative impact of on forecast skill of satellite data and all conventional data. So that's dominated by radiosondes, but there's also some aircraft data in there and surface obs. And you can see if you removed all of the radiosondes globally, you would have a really large, the green line is showing the impact from removing all of those radiosondes. And you can see that, it may not be a huge impact, but it's extremely significant. And one thing that this is not showing, because it's a relatively short period of time this was run over, is the impact of the anchoring that I mentioned earlier. If you ran this for a year, the impact of the radiosondes would be much, much larger because the radiance observations themselves would drift, and the radiance observations are what are providing a lot of the additional impact. And you can see in the southern hemisphere that because of the relative sparsity of upper air observations, the impact on global forecast scores are actually pretty low. And the satellites actually doing most of the work in terms of impact. We have other ways of looking at observation impact. So this is from GMAO. They actually run the same model as us, so this is a really good comparison, a valid comparison for us too. You can see out of all of the observation impacts from the various observation types, by far the largest is the AMSU-A. That's because there's 5 satellites observing all around the globe, and they have that, and they're the only game in town in the southern hemisphere, so they are the biggest impact. But the second most important observation type are the radiosondes, and the next slide actually breaks this down by height and actually compares radiosondes with aircraft. So you can see the radiosondes have a much larger impact than the aircraft do, mostly focused in the lower to mid troposphere. And so, in summary, upper air observations are the backbone of our observation systems, both through direct impact of the observations on the analysis and as an anchor for those observations. we have a number of current challenges, which I didn't mention in the rest of the talk. One of them is the pack to buffer conversion that we're finally getting to the end of. And the other one is we've got a lot more high vertical resolution measurements that we've not been using up till now. So thank you for your patience and your attention, and I'm happy to take any questions.
Yeah, no, thank you. We got one question that came in the chat, and then we'll get on to our next speaker there. But real quick, and then Tom's got his hand up, and he's going to be our next speaker. So I'll ask this question, then Tom, you can ask yours, and you can go right into your talk. So the question was about like long-term outages at a site where we start missing flights. What real impact does that have on this process?
Mostly it depends on where the site is. As you can see, we are an ecosystem. It's definitely an ecosystem of observation. So often a single outage is very hard to see, especially if it's in a very data-rich area. I'm not saying though that every single observation is important. But yeah, we often actually get the question, if we lose X, what will the impact on the forecast be? And one thing I didn't really expand on when I was speaking earlier is, and the reason I didn't show any individual case studies is it's statistical.
Okay.
You know, it's very you very seldom see can connect a single observation outage to a single forecast bust.
Okay, outstanding.
It's something that tends to happen over, you only see if you really run a very long period of time, given how robust our system is.
Okay, good deal. Thank you very much for that. Thank you for getting all that information in such a quick time there. Really appreciate that. Tom, go ahead and ask your question. Like I said, go ahead and get into your presentation there, and Tom's going to try to kind of get us a little bit closer to back on track. So, Tom, go right ahead.
So, Andrew, I got a question about the SONs now not having pressure cells. I know maybe it's not your expertise, but how do you feel that may impact, or if it will, if it's just using the GPS to figure out GPA heights?
I think it would mean part of our QCs becomes a lot more tricky. I would, to be honest, I would need to work. I don't have a quick answer to that. It's, a large amount of our QC involves cross-checking between the various parameters. So it could be a problem, but I would need to come back to you on that one.